In the last video, we talked about how to simplify and solve integrals utilizing partial fractions. And in this video, we're going to talk about a little bit more advanced partial fraction simplification. So let's say you have an integral which looks like this. Now you may think that in order to break this down, you might have a over x plus 2 cubed plus b over x minus 2 plus c over x squared. And if you thought that, you'd be wrong. Maybe you thought that it was a over x plus 2 plus b over x plus 2 plus c over x plus 2, right? Because you have three of them. But no, but the technique that you use when you have multiple factors of a simplified expression is to go a over, right, x plus 2 cubed, right, just like so with the first one, and then to continue but individually break off a factor until you don't have any more. So we're going to do squared now, and then we're going to do it one more time with just x plus 2, right, and we're going to go d over x minus 2, and then for x squared, right, we're going to have e over x squared plus e over, and we break off a factor, we'll do f over x, right? And that's the way we would break it down, and then we would continue to, you know, multiply a by each one of those and then solve for a, b, c, d, and f, which you can guess becomes very tiring. There's a lot of different repeated fractions that you would have to do, right? Let's just do one more example, and I'm not going to solve these, I'm just going to show you. So maybe we have an x cubed and an x plus 1 squared and an x plus 4 cubed, right? I'd start with the first one, so we'd have a over x cubed, and because it is as simple as possible, I have to break off a factor, right? And then I'm going to do it again until I have no more factors. Then I'm going to get x plus 1 squared, break off a factor, get x plus 1, just like that. And then I did the same exact thing for x plus 4, but I'd go x plus 4 cubed, x plus 4 squared, and then just x plus 4. And so that's how you would do that. Now let's say you have an integral which looks like this. Your instinct might be to say a over x squared plus b over x, and if you got that far, you would be correct. But the issue is this right here is what we call an irreducible quadratic factor, right? We have some quadratic, you have this squared right here, but this can't be reduced any further into anything like x plus some number times x plus another number, right? If we do 1 and 1, we'll end up with this 2x in the middle, but we'll end up with a 1 at the end. We can't do 2 and 1 because then we'll end up with a 3 in the middle. So this is an irreducible factor. And generally the way that you deal with irreducible factors is by having a numerator in this form. Cx plus d over that irreducible factor, x squared plus 2x plus 2, right? Just like that. And then from there, let's say, for example, that this was squared, right? Let's just say that was squared. You would add, so you have your squared one right here, and then you would add ex plus f over x squared plus 2x plus 2, right? You don't add the squared because you did an individual factor. So that's the way that you would do partial fraction decomposition if you had a quadratic, an irreducible quadratic factor right here. You'd have that x there. And then what you can do is you can set up your numerator. You'll say that, you know, a times x times that fraction times that function plus b times that function times that function times that function, and so on, is all going to be equal to 1. And then you can set up this massive chain of simultaneous equations, and you can solve for each one of your parts.